problems from the sheet titled parity. Sheet titled parity. Let us get hands-on with issues related to parity. That is even and odd. That's the name. So, the first problem is about numbers from 1 to n, 1 to 101. Numbers from 1 to 101. These are numbers from 1 to 101. Now the question is, there are only plus signs that I have placed here. Can I change some of these signs? Can I change some of these signs so that the summation becomes 0? Can I change some of these signs so that the summation becomes 0? That's a question, right? Some of these pluses I want to replace by minuses so that the algebraic sum is 0. Now, forget that for a while. Let me just look at the parity of this. Because no matter how I change the signs, the parity will be preserved. Right? If this is even, it will remain even no matter what signs I change. If it is odd, it will remain odd. Yes or no? Now, sum of the first 101 natural numbers, which is 101 into 102 divided by 2. Yes or no? Yes or no? N into n plus 1 by 2, sum of the first 10 natural numbers. Have I told you that? 1 plus 2 plus 3 up to n is n into n plus 1 by 2. N into n plus 1 by 2, which is like 101 into 51, which is an odd number. Yes or no? Product of two odds is an odd. Product of two odds is an odd. Which means now, if I change some signs here, the value will change, but the parity will remain odd. That means it can never be 0. It can never be 0 because 0 doesn't belong to an odd parity. 0 belongs to an even parity. So this summation can never be 0 no matter in what manner I change these, some of these plus signs to minus. No combination will ever produce 0 out of this. No combination will ever produce 0 out of this because of parity considerations. Yes or no? The second problem of the sheet is about a collection of 101 identical looking coins. We have 101 identical looking coins. They are not identical, but they look identical. Some of these coins are fake. They are counterfeit. They are fake. The situation says that out of these 101 coins, 51 coins are fake. 50 coins are fake. It says that 50 coins are fake. And there are obviously then 51 genuine coins. (51 genuine coins). 50 coins are fake and 51 are genuine coins. Right? Now, from this set, I pick a coin randomly. I pick a coin randomly. A certain coin C is picked. Now I have a machine of balance, a weighing machine, right, which is capable of telling me the difference in the weights in the two pans. It tells me the difference in the weights in the two pans. This machine, I can place coins in the two pans, and this machine can tell me the difference. It's calibrated to tell me the difference between the weights in the two pans. This is how this machine is calibrated, right? You know what I'm saying? Sorry? No, we will assume not. We will assume not. We will assume that there are. Of course, yes. Of course, yes. That will be the difference. But how will it make a difference? Okay, because you do not know the actual weight of any coin. Then it will tell me the weight of that coin. Surely it will tell me the weight of that coin. So all that it is calibrated to do is to measure the difference between the weights in the two pans. Okay. Now all that I am allowed is one weighing. And in that one weighing, so I can do anything that I want to with this set of 101 coins, which includes this coin, see that I have picked, which I want to determine for genuinity, right? And in one weighing, I want to figure out whether this coin C is genuine or counterfeit, genuine or fake, right? Now, the problem also says that the fake coin, if a good coin, that means if a genuine coin, the problem also says that if a genuine coin weighs W grams, if a genuine coin weighs W grams, right? There are 51 of these genuine coins. If a genuine coin weighs W grams, then a fake coin would weigh either W plus 1 gram or W minus 1 gram. All that we know is that the fake coin differs by a gram, The fake coin differs by a gram. Right? Now, we want to, I have picked a coin randomly from this, right? A coin C. I want to determine whether it is fake or genuine. So if I picked a coin C, then there are 100 coins left. Out of 101 coins, there are 100 coins left if I have picked one coin C, right? Let's say the remaining 100 coins are C1, C2, C3, C100 are the remaining 100 coins. C1, C2, C3, C100 are the remaining 100 coins. This is the 101st coin, and I want to determine whether C is genuine or fake. Okay. Now, what I do is I break these 100 coins into two groups of 50 coins each. I break this into two groups of 50 coins each, right? Say W1, for example. I place 50 coins here and I place 50 coins there. I place 50 coins, that means W1 is C1 plus C2 plus C50. In one of the pans, I place 50 coins, C1 plus C2 plus C3 plus C50. And in the other pan, the remaining 50 coins, that means C51 plus C52 plus C100. This is what I do for the second pan, right? Now, there is some calibration here which will give me W1 minus W2. So I would have knowledge of W1 minus W2. So what is known to me is W1 minus W2. What is known to me is W1 minus W2. That means I have known C1 plus C2 plus C50 minus C51 plus C52 plus C100. So this is the reading which is known to me. This is the reading, right? This is my reading which is known to me. And it will have a certain parity, even or odd, which I would know, right? Which I would know. Now, suppose W was the weight of the true coin. Suppose W was the weight of the true coin, right? Can I write all of this as C1 minus W plus C2 minus W plus C50 minus W minus C51 minus W, C52 minus W, C100 minus W. Can I do this? See, the minus W will get cancelled with a plus W. So there is no issue with this. Do you understand what I'm saying? W, so each of these coins, each of these Ci minus Ws would either be 0 or plus 1 or minus 1, yes or no? Difference between the weight of a coin and W would either be plus 1 or minus 1 or 0. Yes or no? You know what I'm saying? If Ci is a true coin, is a good coin, then Ci minus W would be 0. If Ci is a good coin, then Ci minus W would be 0, because a good coin weighs W grams, right? And these C1, C2, C3 are respective weights of the coins, by the way, just to avoid discomfort. These are the weights of these coins. C1, C2, C3, C100 are the weights of the 100 coins, right? Some of these Ci's would be W. Some of these Ci's would differ from W by 1. Ci's are the weights of the various coins. Some of these Ci's would be W if they are true coins. The fake coins would differ from W by 1 unit. Yes or no? So then, this difference would have either an even parity or an odd parity. This difference, this minus this, would have an even parity or odd parity. I have knowledge of this number. I have knowledge of this number. Therefore, the reading tells me whether this is even or odd. Yes or no? Now, if I change this minus sign to plus sign, will the parity change? It will have the same parity. If the reading had shown an even number, then this plus, on replacing that minus with this plus, I will still be able to see an even number. If that difference, earlier difference, was an odd number, which is reflected by the balance, then this will also be odd on replacing the minus sign with a plus sign. Yes or no in the first place? Right? Sure about it? Now, there are only two possibilities for C. C could be fake or C could be genuine. C could be fake or C could be genuine. Now, let's explore both of them. So in any case, I have knowledge of the parity of this summation. I have knowledge of the parity of this summation. Now, suppose case 1, C is fake. And C doesn't belong to this set, by the way. I have excluded C from this set, right? Suppose C is fake. Then in this set, there will be 50 fake coins, 51 genuine coins, and 49 fake coins. Yes or no? Suppose this was fake. Then in this set, I'll have 49 fake coins and 51 genuine coins. Yes or no? Right? That means if C is fake, then in S there would be 49 fake coins, and in this, right, some of these CIs, 49 of these CIs would be fake and 51 of these CIs would be genuine. Yes or no? 51 of these CIs would be genuine, right? That means if there are 51 genuine, then see, all these numbers are of the form Ci minus W, where I can be 1, 2, 3 up to 100, right? Now, every time I is about a number which is genuine, then Ci minus W would be 0. If a Ci represents a genuine coin, then Ci minus W would be 0. That means 51 of these numbers would be 0. 51 of these numbers would be 0. That means there are 100 Ci minus Ws here, isn't it? There are 100 Ci minus Ws here, out of which 51 are about genuine CIs. So 51 would be 0. 51 of these 100 numbers would be 0. So out of these 100 numbers, 51 of the Ci minus Ws would be 0. Yes or no? 51 would be 0 and 49 remaining, 49 would be plus 1 or minus 1, depending on whether the fake coin is a gram more or a gram less, right? So 49 of these Ci minus Ws, 49 of these Ci minus Ws would be plus 1 or minus 1. That means in the summation, 51 of these brackets will add up to 0. 49 of these brackets would add up to would be either each plus 1 or minus 1. That means the sum S would be odd, because 49 plus 1s or 49 minus 1s would be an odd number, right? That means this sum S would be odd, because 49 plus 1s or minus 1 and 51 zeros. So the sum would be odd. Now if the sum S is odd, then the original difference that we started with would also be odd. That means if the difference is odd, then we can say that C is fake. If W1 minus W2, which boiled down to S, if that gave me an odd parity, then C will be fake. Yes or no? Do you understand this? Right? Are you confused? See, we knew the parity of this, right? That means originally we started with this. So this told me whether this was even or odd. CIs were the weights of the coins that I have chosen. 100 coins to the exclusion of this, right? Now this difference could have been written Ci minus W plus C2 minus W plus C50 minus W minus, do you understand this? Each of these plus W would get cancelled with minus W, that was this sum. Now the parity of this would be the same as the parity of this, right? I know the parity of this. Let me explore the parity of this. Yes, let me explore the parity of this. Now, if C was fake, that means I have one fake coin out of this. That means in these CIs, there must have been 49 fake coins and 51 genuine coins. If the one that is excluded, see, the fake coin is excluded, then in the remaining 100, 49 must be fake coins here. That means 49 out of these CIs must be fake and 51 of these CIs must be genuine. Now, that means look at Ci minus W, right? 100 such numbers appear here. Ci minus W, I equal to 1 to 100, of which 50 will be 0. 51 will be 0. Why would 51 be 0? Because 51 are genuine. So every time Ci is genuine, Ci minus W would be 0. So 51 of these numbers would be 0. And the remaining 49 would be plus 1 or minus 1 in this summation. That means if the remaining 49 are plus 1 or minus 1, that means the sum of this this sum S would be an odd number. That means if C is fake, then this is odd, and then this difference will also be odd. So if the difference exhibited by the scale is an odd number, then you can conclude that the one that you have chosen out is fake. Yes or no? Suppose, just to explore, suppose C is genuine. Can I wipe this off? Suppose C is genuine. The one that I have picked out is genuine. Case 2. C is genuine. Suppose C is genuine. Then in this collection of CIs, one genuine coin is excluded. There are 50 fake coins and 50 genuine coins. That means 50 CIs in this set, 50 CIs in this set are fake, and one genuine coin is excluded. So 50 CIs are genuine. Now, that means 50 of these Ci minus Ws are 0. Because 50 genuine coins, each will weigh W grams. So 50 of these Ci minus Ws would be 0. And 50 of these Ci minus Ws would be either plus 1 or minus 1. That means this summation would be an even number. This summation would be an even number, 50 into 1. Right? That means if S turns out to be even, so then S will turn out to be even if this is the case. If S is even, then this will be even. That means if the difference turns out to be even, then the coin C must be genuine. So based on the parity of the difference, exhibited by this scale, we can suggest whether C is even or odd. Whether C is even or odd. Do you all understand this? Right? Very powerful tool, isn't it? And it's all based on parity. Clear? We want all integer solutions to this equation. We want all integer solutions to this equation. X and y are integers. Now, very clearly, between x and x plus 1, one of them must be even. Between x and x plus 1, one of them must be even. They are consecutive integers. Therefore, the left hand side is even. Yes or no? But look at the right hand side. This is cube of an odd number. So this is odd. Cube of an odd number would be odd into odd. So that makes it odd. So right hand side is odd, left hand side is even if x and y are integers. Therefore, there are no integer solutions to this equation. There are no integer solutions to this equation. There are no integer solutions because the parity of left hand side is even if x is an integer, and the parity of right hand side is odd if y is an integer. Yes or no? Right? So this is not possible. See, first of all, you understand what a gear is. You know, these are essentially two circular entities. They have teeth. They have teeth in them. And they always rotate in opposite directions. If one is rotating clockwise, the other one must rotate anti-clockwise. If there are two gears, then, and if they are in contact, they will rotate in opposite directions. They will rotate in opposite directions. Such is a gear mechanism. Such is a gear mechanism. Right? Now, what the problem says is there is a collection of gears rotating in tandem. One gear, 3 gears, 4, 5, 6, 7, 8, 9, 10, 11 say. These are 11 gears. Is it possible to have this or not? Let's say if this gear, let me say there are two states of rotation. 1 and 0 are two states of rotation, right? One clockwise, the other one anti-clockwise. Let me start with this. If this is state 1, this must be state 0. This must be state 1. This must be state 0. This must be state 1. This must be state 0. State 1, state 0, state 1, state 0, state 1. 1 and 1. Is it possible? Two neighboring gears in the same state? Not possible. However, if instead of 11, if I had 12 gears, then it would have been possible. If I had 13 gears, not possible. If I had 14 gears, possible. That means every time if the number of gears are odd, it is not possible. If the number of gears are even, it is possible. Yes or no? Right? So the given situation is not possible because 11 is an odd parity. Now in the sixth problem, what's given is k an even number. K an even integer. That's given. Is it possible to write 1? Is it possible to write 1 as the sum of reciprocals of k odd integers? I want to write 1 as the sum of reciprocals of k odd integers. A1 is odd, A2 is odd, A3 is odd, AK is odd. I want to write 1 as the sum of the reciprocals of k odd integers. Is it possible? No. These are where k is an even number and these k integers are, each of them is odd. All of these AIs are odd numbers. All of these AIs are odd numbers. Now, suppose I have n, which is A1, A2, A3, AN. Suppose that's n. AK. AK. Capital N is the product of all these odd numbers. Then capital N will be odd. Yes or no? Because AIs are odd. So this is odd. This is odd, right? Now if I multiply throughout by A1, A2, A3, AK, that means the left hand side would be n. Right? The right hand side would be n divided by A1. This would be n divided by A1. This would be n divided by A2. I am multiplying throughout by n. N by A1 would be A2, A3, AK. N by A2 would be A1, A3, A4, AK. N divided by A3 would be, again, you know, A1, A2, A4, etc., AK. Isn't it? And the last number would be n by AK, which would be A1, A2, AK minus 1. Yes or no? Now, n is odd. Left hand side is odd, isn't it? Because n is this. Now, each of these are odd numbers. This is odd O1. Product of odd numbers? So this would be odd. This is product of odd numbers? This would be odd, isn't it? Product of odd numbers? Odd. Product of odd numbers? Odd. How many odd numbers are there? K odd numbers? Even number of odd numbers? But if an even number of odd numbers would be an even number. So this is even. I have even numbers of odd numbers. K is even, that's given. I have even number of odd numbers and therefore they add up to an even number. So odd equal to even. Is this possible? That means this proposition is invalid if k is even. Perhaps the simplest. Can the sum of first n natural numbers be a prime number? You know, there are two kinds of numbers, prime and composite. Prime and composite. Can this be a prime number ever for n belonging to the set of natural numbers? Can this be prime? N greater than 1. N equal to 2? Okay. So, for more than 2, can this ever be a prime? Can this ever be a prime? Why not? How do you know? Was it just a guess that for 1 and 2, for 2 only? For n equal to 2. Oh, so those are all conjectures. You just made guesses because it didn't add, 20 numbers didn't add up to a prime. You assume that, you know, no sum beyond 2 will add up to a prime. You just assumed that. Really? Always? Always even? No. Okay, we need to check if this can ever be a prime. That means whether, see, a number would be composite if I can break it up into a product. If I can break it up into a product of two integers in which one of them is not 1. If I can break it up into a product of two integers in which one of them is not 1. I mean, it's not like I say 5 is 5 into 1. So 5 is composite, no. Prime numbers are basic building blocks of numbers. They cannot be further fragmented. Right? I want to check if this will ever be a composite number or not. It's a very easy thing. Sum of the first n natural numbers is what? N into n plus 1 by 2. Yes or no? So far so good? Now, between n and n plus 1, 1 must be even because they are consecutive. One of them must be even. One of them is even, right? That means between n and n plus 1, one of them will be divisible by 2. The other one would be odd, right? So suppose n is divisible by 2. Suppose n is even. Then this is like n by 2 into n plus 1. I'm assuming n greater than 2. All right? I'm assuming n greater than 2. So this is n by 2, which would be an integer, into n plus 1. Hey, it's product of two integers. Product of two integers, therefore it's a composite number. Therefore it's a composite number, right? So when n is even. Suppose when n is odd. If n is odd, then n plus 1 will be even. Then n plus 1 will be divisible by 2. Then n plus 1 by 2 will be an integer. Then it can be written as n into n plus 1 by 2. So again product of two integers. Because now n plus 1 by 2 would be an integer. Why? Because n plus 1 will be even and therefore divisible by 2. Yes or no? Right? So product of two integers, therefore again a composite number. Therefore it's not prime. It's not prime. For n greater than 2, sum of n natural numbers will not be a prime number. Will never be a prime number. It will always be a composite number. It will always be a composite number because it can be expressed as product of two integers. When n is even, n by 2 would be an integer. So integer into integer. When n is odd, n plus 1 would be an integer. Then n plus 1 is divisible by 2 and n plus 1 by 2 would be an integer. So integer into integer. Therefore, it's a composite number. Yes or no? The problem is pretty straight actually. Find all positive integers n for which these three are prime numbers. Right? Now, if you really add these three prime numbers, 3n minus 4 plus 4n minus 5 plus 5n minus 3. What does it turn out to be? 12n minus 12. Which is an even number? Because this is divisible by 2, this is divisible by 2. It's an even number. Now, if these are all primes, and if none of them is 2, if these are primes and none of them is 2, that means these must be odd primes. If none of them is 2, then they must be odd primes, and sum of 3 odd numbers cannot be an even number. That means conclusion number 1, one of them would have to be 2. Exactly one of them would have to be an even number. The other 2 are odd numbers. The other 2 odd numbers add up to an even number. When added to 2 will give me an even number. If sum of 3 odd primes is adding up to an even number, that means one of them has to be 2. Right? Otherwise, if they were all odd, then their sum would have been odd. Yes or no? That means one of them has to be an even number, and the only even prime is 2. Now, this or this, one of them would have to be an even number. One of them would have to be an even number. One of them would have to be an even number. Which one would be an even number? Which one would have been an even number?
3n minus 4, because if then there is 4 is divisible by 4 is an even number, and if n is an even, then the total number is even.
See, one of them, which one would be an even number? 5n minus 3 or 3n minus 4 or 4n minus 5? For, okay. So which of them could be 2 then? One of them would have to be 2. 3n minus 4 would be 2.
If 4n minus 5 or 5n minus 3 is 2, then 4n equals to 7 or 5n equals to 5.
So which of them would be even? Only one of them would be 2. Which one? See, this cannot be 2, because this is even minus odd. This is even minus odd, and this cannot be 2. That means either this must be 2 or this must be 2. Yes or no? That means either 3n minus 4 must be 2, or 5n minus 3 is 2. This couldn't have been an even number, because this is even minus odd, this is odd. That means either 5n minus 3 is 2 or 3n minus 4 is 2. This will determine the value of n. That means this will give me n equal to 2. This will give me n equal to 1. So I need to check only for 2 numbers, n equal to 1 and 2. Now n equal to 1 I rule out. You can check that. Right? N equal to 1 I rule out. Because again n equal to 1, these two are negative. These two are negative and they are equal. Right? So I need to just check for n equal to 2. So for n equal to 2, this will become 2. This will become 3. And this will become 7, which are prime numbers. Yes or no? So n equal to 2 is the only solution, and these prime numbers would be 2, 3 and 7. Yes or no? So there is uniqueness established. There is no other value of n. Simple premises of the 3 numbers, since they add up to an even number, one of them would, not all can be odd, because 3 odd numbers would have been an odd number. Therefore, one of them would have been an even number. So one of them must have been an even prime. This cannot be an even number because it's even minus odd. So either this is even or this is even. This, and the only even prime can be 2. That means even means it has to be 2. That means either this is 2 or this is 2. If this is 2, this gives me n equal to 1. If this is 2, this gives me n equal to 2. n equal to 1. By substituting, you can eliminate. This will give me identical numbers, right? And n equal to 2 therefore works good for us. N equal to 2 gives me set of numbers 2, 3 and 7. This will become 2, this will become 3, this will become 7.